Welcome, folks, to the 2023 Design Expo. My name is Ryan Verbrugge, a second-year robotics engineer.
And my name is Ian Mattson, a third-year electrical engineer.
We are members of the Robotic Systems Enterprise working on the AutoDrive 2 challenge. AutoDrive is a 4-year autonomous vehicle competition hosted by SAE and General Motors. This past summer, our team competed with a surrogate autonomous vehicle called the Perception Cart. This cart was outfitted with a LiDAR sensor, multiple cameras, a hyper-accurate GPS, and loads of computers to process and score all of our data. Overall, our concepts paid off with our team returning to Houghton with 4 new trophies to add to our collection. With that, our sights were set on the 2022-2023 academic year, with our main goal being to implement the technology developed for the Perception Cart onto our donated Chevy Bolt EUV that will be used for the remainder of the series. The goals for this year's challenge are basic vehicle integration, simple controls testing for autonomous driving through a mock city, and robust perception systems to detect and react to all possible obstacles. To accomplish these aggressive goals, our members are sorted into several sub-teams based on their interests and technical goals. The mapping team was able to set up and use the donated Novatel PowerPack 7 GNSS and to test the localization system for the car. Using the perception card on campus, the error in the GPS was found to be 1 centimeter standard deviation error when paired to the Michigan Department of Transportation calibration network. In the spring semester, the team was given a high-definition map of the competition track. The mapping team members were tasked with creating a way the vehicle could use the map to follow turn-by-turn instructions. They chose to create waypoints every few meters so that the vehicle's position can be paired against the desired route in the pure pursuit controller, giving the vehicle the best opportunity to maintain its lane position. The perception team was responsible for developing systems to detect street signs, traffic lights, pedestrians, vehicles, and deer. Our sponsor Cepton provided us with a Cepton X90 LiDAR sensor to additionally determine the range and motion of all obstacles. LiDAR is useful as it can accurately report to the vehicle the distance of objects so the vehicle can have enough time to react. Here you can see the team's clustering algorithms be able to recognize objects of interest and make a bounding box around it, indicating a keep-out zone for the vehicle to not enter. Euclidean clustering methods were utilized by the team to efficiently calculate the target obstacles while eliminating background noise, the ground, and other trivial objects. To identify traffic lights and street signs, our team uses a machine vision camera paired with a neural network model called YOLO V5. That has been trained on thousands of test images from datasets and our own data from competition to recognize various traffic light states and all the signs at M City. YOLO was chosen for the incredible number of items it can be trained to classify at once, enabling the vehicle to see and classify all obstacles that it encounters.
The build team is responsible for designing and creating the infrastructure used to convert the team's vehicle from a stock Chevy Bolt EUV to a custom autonomous vehicle. The team worked on applying roof rails and determining the best mounting pattern to bolt the sensor suite to the roof. The sensors needed to be safe, secure, and hot swappable, so the roof mounting system has to be easily removable but still strong enough to withstand vibrations from bumpy Michigan roads. To run the cables from the vehicle's server to the roof of the car, the team decided the best route was to expand the already existing antenna hole just above the rear headliner and add weatherproof grommets to ensure our cables can safely route outside the vehicle and be weatherproof while ensuring that the cabin stays dry. Additionally, a circuit board breakout was developed to accommodate the custom CAN connections to control the vehicle's movements. This is then adapted to interface with multiple computers, including the D-Space Micro Autobox 3, chosen for advanced vehicle control. This prototype board will be replaced with a final revision shortly after the conclusion of the school year, as its proof of concept was a smashing success. Lastly, the team also conducted noise and heat tests on the provided Intel server that will be mounted in the rear of the vehicle. Due to its loud fans and extreme heat, the team is able to use cooling ducts and noise insulation to maintain occupant comfort and optimum server performance during autonomous driving. Our AutoDrive team relies heavily on simulated scenarios to test algorithms and autonomous driving logic, along with the sensor field of view analysis. We use MathWorks tools in MATLAB and Simulink to use a simulation package provided by our competition organizers. By leveraging our simulation abilities, our team is able to design for the future. Lastly, we have our controls team. Their job is to use Simulink with the D-Space Micro Autobox 3 to design safe models that actuate the vehicle's acceleration and brake controls, along with the steering module. Our team's greatest innovation for this auto drive competition series is the creation of a hardware-in-the-loop dyno that the vehicle can be mounted to. As our team does not have access to a test track, and with Uber weather putting a damper on testing, we've been able to retrofit a hub-mounted dynamometer to allow for steering and acceleration simultaneously. This is designed and calibrated with a different Chevy Bolt in the fall semester, and we welcomed our new EUV onto the dyno in spring as soon as we'd arrived to enable the team to simulate driving scenarios virtually, all while actuating the vehicle hardware just as if it were on the road. This enables our team to test a multitude of scenarios throughout the harshest of winters to be prepared for competition in summer. Steering control was tuned on the dyno in early spring. Once we were satisfied, we completed the initial vehicle integration challenge in Lot 24 by the SDC for the vehicle's first non-dyno test. For the integration test, the vehicle demonstrated its autonomous steering capabilities, then demonstrated acceleration to a target speed and braking back to a complete stop. Thanks to the extensive dyno testing, the motion tests for the integration challenge were another smashing success that validates our hard work in designing, calibrating, and using the dyno for advanced autonomous vehicle development. I could not be prouder of the team this year for their amazing effort in getting the car moving in team's record time.
Our future work beyond the end of the semester includes integrating all subsystems for auto drive into the vehicle and performing testing ahead of the June competition in Ann Arbor, Michigan. Additionally, we want to expand our simulation capacities to have automatically scoring systems that can evaluate vehicle performance on and off the dyno setup to identify areas for improvement in perception and motion planning. Lastly, we're working on refining the interior of the vehicle to make it as clean and comfortable as possible, with the target goal of hiding all the autonomous equipment so it appears as close to a standard vehicle cabin as possible. On behalf of the Robotic Systems Enterprise and our Auto Drive Challenge 2 team, Prometheus Borealis, we'd like to thank our competition sponsors for all they do to support us. We'd also like to thank our advisors, Dr. Jeremy Boss and Dr. Darrell Robinette, for all their support of our students and our success. Thank you, folks, for your time, and happy Michigan Tech Design Expo 2023.